Verification with examples. Let's try specific values for a and b. Example 1. A dot equals 7, b equals 3, both odd. Numerator. Undo. Settings window. Narrator. Toggle. Microsoft David. English.
Choose a voice. Combo box. Microsoft Ravi. English. Real numbers 1 RD Sharma. Word window. Question 1 explanation. Verification with examples. Let's try specific values for a and b. Example 1. A dot equals 7, b equals 3, both odd. Numerator. A plus b and numerator. Over 2 equals numerator. 7 plus 3 and numerator. Over 2 equals 10 half s equals 5 open pan node. Numerator. A minus b and numerator. Over 2 equals numerator. 7 minus 3 and numerator. Over 2 equals 4 half s equals 2 open pan 1. Result. One value is odd. The other is even. Example 2. A dot equals 9, b equals 5, both odd. Numerator. A plus b and numerator. Over 2 equals numerator. 9 plus 5 and numerator. Over 2 equals 14 half s equals 7 open pan node. Numerator. A minus b and numerator. Over 2 equals numerator. 9 minus 5 and numerator. Over 2 equals 4 half s equals 2 open pan 1. Result. One value is odd. The other is even. The problem states. A and b are two odd positive integers such that a dot greater than. You need to show that when the expression's numerator, a plus b and numerator, over 2 and numerator, a minus b and numerator, over 2 are evaluated. One of them is an odd integer, and the other is an even integer. Key concepts. Odd integers are numbers like 1, 3, 5, 7, which cannot be evenly divided by 2. Remainder is 1. The sum of two odd numbers is always even. The difference of two odd numbers is always even. An even number divided by 2 results in an integer. Step-by-step proof. Let a dot equals 2m plus 1 and b equals 2n plus 1. A and b are odd integers, so they can be written in the form 2m plus 1 and 2n plus 1, where m and n are integers. Sum of a and b. A plus b equals open paren 2m plus 1 close paren plus open paren 2n plus 1 close paren equals 2m plus 2n plus 2 equals 2 open paren plus n plus 1 close paren. This is an even number. Dividing by 2. Numerator. A plus b and numerator. Over 2 equals m plus n plus 1. M plus n plus 1 is an integer, and whether it is odd or even depends on m and n. Difference of a and b. A dot minus b equals open paren 2m plus 1 close paren minus open paren 2n plus 1 close paren equals 2m minus 2n equals 2 open paren minus n close paren. This is also an even number. Dividing by 2. Numerator. A minus b and numerator. Over 2 equals minus n. Minus n is an integer, and whether it is odd or even depends on m and n. Conclusion. The sum of two odd numbers is even, and dividing it by 2 gives an integer. The difference of two odd numbers is also even, and dividing it by 2 gives another integer. One of these integers is odd, and the other is even. Let's address all questions sequentially. Each will have the question, examples for explanation verification, and a detailed proof. Question 2. Prove that the product of two consecutive positive integers is divisible by 2. Example, explanation and verification. Let the two consecutive integers be n and n plus 1. In any two consecutive integers, 1 is always even, divisible by 2. The product n plus 1 will therefore include an even number, making it divisible by 2. Verification. N equals 3 plus 1 equals 4. 3 times 4 equals 12. Divisible by 2. N equals 6 plus 1 equals 7. 6 times 7 equals 42. Divisible by 2. Let n be any positive integer. If n is even, n equals 2k, and the product is n plus 1 equals 2k plus 1 which is divisible by 2. If n plus 1 is even, n equals 2k minus 1, and the product is n plus 1 equals 2k minus 1 2k which is divisible by 2. Thus, n plus 1 is always divisible by 2. Question 3. Prove that the product of three consecutive positive integers is divisible by 6. Example, explanation and verification. Three consecutive integers n plus 1 plus 2 will always contain one even number, divisible by 2. One number divisible by 3. Their product n plus 1 plus 2 is therefore divisible by 2 times 3 equals 6. Verification. N equals 4 plus 1 equals 5 plus 2 equals 6. 4 times 5 times 6 equals 120 divisible by 6 N equals 7 plus 1 equals 8 plus 2 equals 9. 7 times 8 times 9 equals 504 divisible by 6 Proof. Among three consecutive integers n plus 1 plus 2, at least one is divisible by 2, even. At least one is divisible by 3. Therefore, their product n plus 1 plus 2 is divisible by 2 times 3 equals 6. Question 4. For any positive integer n, prove that n cubed minus n is divisible by 6. Example, explanation and verification. Factorize n cubed minus n. N cubed minus n equals n minus 1 plus 1 This is the product of three consecutive integers, proven divisible by 6 in question 3. Verification. N equals 4. N cubed minus n equals 4 cubed minus 4 equals 6 4 minus 4 equals 60 divisible by 6 N equals 5. N cubed minus n equals 5 cubed minus 5 equals 5 minus 5 equals 20 divisible by 6 Proof. Using the factorization, n cubed minus n equals minus 1 plus 1 As shown in question 3, the product of three consecutive integers is always divisible by 6. Question 11. Show that any positive odd integer is of the form 6q plus 1, 6q plus 3, or 6q plus 5, for some integer q. Example, explanation and verification. Positive odd integers are not divisible by 2. When dividing any integer by 6, the remainder can be 0, 1, 2, 3, 4, 5. Only 1, 3, 5 correspond to odd integers. Verification. A dot equals 7, 7 equals 6 open parent 1 close parent plus 1. A dot equals 9. 9 equals 6 open parent 1 close parent plus 3. A dot equals 11. 11 equals 6 open parent 1 close parent plus 5. Proof. By the division algorithm, any positive integer a can be written as a dot equals 6q plus a equals 0, 1, 2, 3, 4, 5. Odd integers are those where equals 1, 3, 5. Question 12. Show that the square of any positive integer cannot be of the form 6m plus 2 or 6m plus 5. Example, explanation and verification. Square all integers x. X squared can only result in 6m, 6m plus 1, 6m plus 3 or 6m plus 4. 6m plus 2, 6m plus 5 are not possible. Verification. Z equals 2. X squared equals 4 equals 6 open parent 0 close parent plus 4. Z equals 3. X squared equals 9 equals 6 open parent 1 close parent plus 3. Proof. Let z equals 6k 6k plus 1 6k plus 2 6k plus 3 6k plus 4 6k plus 5. Square each. Open parent 6k close parent squared equals 36k squared equals 6m. Open parent 6k plus 1 close parent squared equals 36k squared plus 12k plus 1 equals 6m plus 1. Open parent 6k plus 2 close parent squared equals 36k squared plus 24k plus 4 equals 6m plus 4. Open parent 6k plus 3 close parent squared equals 36k squared plus 36k plus 9 equals 6m plus 3. Open parent 6k plus 4 close parent squared equals 36k squared plus 48k plus 16 equals 6m plus 4. Open parent 6k plus 5 close parent squared equals 36k squared plus 60k plus 25 equals 6m plus 1. 6m plus 2 6m plus 5 are not possible. Question 15. Show that the square of an odd positive integer is of the form 6q plus 1 or 6q plus 3. Example, explanation and verification. Odd integers can be written as 2m plus 1. Squaring gives x squared equals 4m squared plus 4m plus 1 equals 2 open parent 2m squared plus 2m close parent plus 1. Verification. Z equals 3. X squared equals 9 equals 6 open parent 1 close parent plus 3. Z equals 5. X squared equals 25 equals 6 open parent 4 close parent plus 1. Proof. Let z equals 2m plus 1. X squared equals open parent 2m plus 1 close parent squared equals 4m squared plus 4m plus 1. Rearrange. X squared equals 2 open parent 2m squared plus 2m close parent plus 1. Since 2m squared plus 2m is an integer, x squared equals 6q plus 1 or 6q plus 3. Taskbar, OBS